Experiment 9, gas laws, absolutely directly relates to chapter 5 in the textbook. So hopefully you have done that recently or are doing it right now so that this will absolutely support your learning in the lecture. So imagine this. You've experienced some of these things in regular life. How come the sides of deodorant cans and other aerosol cans say don't dispose of in fire? And maybe you haven't tried this one, but it absolutely led to one of the gas laws in chapter 5. How come a balloon shrinks if you throw it in your freezer? A balloon that has been blown up. Why does it shrink if you put it in the freezer? We're going to explore some of this practical stuff and understand the theoretical basis behind it in this lab. So here are your two goals. You're going to look at a specific amount of gas at a specific temperature and look at the pressure versus volume relationship. And you're also going to look at a specific amount of gas that's held at a constant volume and look at the pressure and temperature relationship as you change the temperature. I may be giving away too much for those who are writing full lab reports for this lab, but here are your goals, otherwise known as the objectives of the lab. So rewrite these in your own word if you're in your own words if you're writing a lab report for this experiment. Just a reminder that there are 3 common states of matter. There are plenty of others that we don't study in detail in 127 or in 151 for that matter. But solid, liquid, and gas are the states that are most commonly interacted with in everyday life. And we're exploring the first one on the left here, gases, this experiment, because the behavior of gases is highly, highly predictable under the conditions in which we live, which are relatively low pressures and relatively high temperatures for a gas. Keep in mind that gases are just liquids that have boiled already, or solids that have melted and boiled already, or solids that have sublimed into gas already. So gases are, for the gas, very hot. They have already boiled into the gas phase. And so when we do experiments with gases, their behavior is predictable so long as we don't have gas crammed into too small of a container, too much gas crammed into a small container, or that it's too cold and approaching becoming a liquid. Where we live at 1 atmosphere of pressure and normal temperatures, 25 degrees Celsius or so, 298 Kelvin, the behavior of gases is generally very predictable, and that's what we're exploring in this lab. So we're going to look at 4 potential variables, although some of them we won't change at a time, so that we only have 2 that are changing at any given time. Pressure, abbreviated capital P, volume, abbreviated capital V, temperature, abbreviated capital T, and amount of gas in moles, abbreviated with a lowercase n. I leave it to you to explore temperature conversions, going from degrees Fahrenheit, that's used in the United States for bizarro reasons, 2 degrees Celsius, to Kelvin. Notice there is no degree for Kelvin. The unit of Kelvin is not degrees. The unit of Kelvin is Kelvin. The pieces of kelvins are called kelvins, not degrees. The pieces of Fahrenheit and Celsius are called degrees, but not so for Kelvin. If you're being specific in your language, which you should be in your reports and in your life so that people know that you know what you're talking about. If we hold any 2 of these 4 constant, the other 2's impact on each other can be explored very, very, very easily. Just a quick reminder, what is pressure? This is straight out of the textbook, that pressure is force per unit area, but we leave that to the physicists to play around with. Gases in the atmosphere colliding with the surface of Mercury will force it up in a column to a height of 760 millimeters. This would be a tube that you would have upside down. You would fill it completely to the top with mercury and then whip it upside down carefully. This is not air up here. This is a vacuum. You whip it upside down into a dish of mercury, and the atmosphere pressure, the gas particles colliding with this mercury, would hold it up in the tube to a height of 760 millimeters. This is why atmospheric pressure in millimeters of mercury is 760. That's equal to 1 atmosphere. Another word for a millimeter of mercury is torr, in honor of Torricelli, who invented the barometer, or was one of the person credited with inventing the barometer. If you're measuring a gas pressure other than the atmosphere, it looks slightly different, but you can still use mercury, and that is technically a manometer, M-A-N-O-meter. There are 4-ish gas laws. Amundsen is another person who's credited with Gay-Lussac's law. And for some very strange reason, your book combines Charles and Gay-Lussac's law together. I do not know why, but here you go. I do not view Chemistry 127 as a history lesson memorizing names and dates, so in my lectures, I don't really care if you know whose law is whose, but your professor may think that that is an important thing to know, so learn it as your instructor so desires. Boyle explored pressure versus volume. Charles explored volume versus temperature. Gay-Lussac explored pressure versus temperature. And Avogadro, as you might imagine from his discovering of the amount of stuff, the mole, looks at volume and amount of material in moles relationship. Boyle's law, we're looking at pressure versus volume. That is one of the laws that we will explore in this lab. This is the only law that we look at that is an inverse relationship, meaning when one goes up, the other one goes down. When one goes down, the other one goes up. This is the only law that we look at that is an inverse relationship. I point that out because a lot of people are trying to memorize. When is that direct? When is it inverse? This is the only inverse one we look at, just so you know. Charles's law is volume and temperature. Not one of the laws that we'll look at today. Notice it is a direct relationship. If one goes up, the other one goes up. If one goes down, the other one goes down. Gay-Lussac's law, we will look at temperature versus pressure, assuming the volume of gas and the amount of gas are not changing. Another direct relationship. One goes up, the other goes up. One goes down, the other goes down. Avogadro, I would argue, is a self-obvious law that if you have more gas, it takes up more space. When you blow up a balloon, it gets bigger. Not too much of a shocker, but got his name on a law for it. Not one we will explore in the lab. Although, as you put more air into the syringe that you will use to perform the experiment, the syringe does get bigger. As you pull back on the syringe and increase the volume, there is more gas in the syringe. It's something that you will practically see, but it is not a relationship that we will experimentally measure. So here's the equipment that you will use. There will be a temperature sensor that you can plug into the lab customer near interface. There was a pressure sensor that you can plug into the lab customer near interface. You can plug them both in at the same time, which we'll use in the second part of the experiment. You can plug the temperature probe in at the beginning if you want to, even though you don't use it in the first part of the experiment. The syringe is just a standard medical syringe, which has a threaded end to it that you could attach to a needle, or you could attach to the fitting on the pressure sensor. The pressure sensor has a valve on it. It is in the open position when the handle is facing this direction, because that is where the hole is. So now air can flow into the pressure sensor and it can measure the pressure. If the handle were turned this way, your experiment would not work because the pressure sensor would then be closed. In the second part of the experiment, we will not use a syringe. We will thread this rubber hose onto the pressure sensor and connect the hose to a glass tube that is sealed at one end. It's just an eyedropper that we've corked one end of, and we'll take the pointy end and shove it into the rubber hose. That will hold a fixed volume of gas that we can change the temperature of by immersing the syringe, the pipette into, or the eyedropper, into ice water or boiling water. With the syringe hooked onto the pressure sensor, we can change the volume of the syringe without changing the amount of air that's actually in it. We'll change the volume, but not change the number of moles of gas by pulling back on the plunger or forcing the plunger in, and see what happens to the pressure. So for pressure volume, you don't need the temperature sensor attached. You just need the syringe attached. As the instructions will show you, you need to set the syringe. If you have a 5 milliliter syringe, you'll set it at 2.5 milliliters before you attach it to the pressure sensor, so that you can back the syringe off to 5 milliliters and see what happens to the pressure, and force the syringe in to 1 milliliter or as 1.25 milliliters, half the volume, and see what happens to the pressure. You'll just read the pressure on the screen. You can change the units if you want to have it in something other than torr, although I don't know why you necessarily would. Torr / millimeters of mercury is totally fine for this experiment. You don't need it in atmospheres. For the pressure and temperature relationship, obviously, you need the temperature probe hooked up along with the pressure probe. You will rubber band the eyedropper to the temperature probe so that you can dunk them into boiling water when it's sitting on the hot plate, or an ice bath that is not shown. For this second part of the experiment, you'll need to record both temperature and pressure on the data sheet. Things to think about. You really want a steady volume on the first part of the experiment. So as you pull the syringe back from 2.5 to 5 milliliters, or squish the syringe in from 2.5 to 1.25 milliliters, it's going to take two hands, because you really want to try and hold that volume as steady as possible so that you can get a steady pressure reading. In part 2 of the experiment, really please make sure that the cables and hoses do not touch the hot plate, because they will melt. It will smell bad, and you will ruin the equipment. As always, mistakes are not valid sources of error, and think about which laws have a direct relationship and which laws have an inverse relationship, and what that means to part 1 of the experiment and part 2 of the experiment. I hope you enjoy it.